Good morning, everyone. I'm Songlin Huang from the University of Hong Kong, and I'm here to present my work, Neutrino, fine-grained GPU kernel profiling via programmable pairing. And this is work done with my best supervisor, Chenshu. Yeah. Profiling the GPU workload, or particularly GPU kernel, the code running on the device, is a critical challenge, but it's very problematic. Since the existing providers are kernel exclusive, you may know the memory allocations, you may know the kernel time, you may know the speed, but you have no way to get inside the devices. It is not fine-grained. Other kernel providers are hardware dependent. For example, if we want to know the heat rate of the cache, we need to implement some hardwares, named the performance monitor unit, which is basically a +1 counters that is triggered accordingly, and we can sample it at an interval, like 1 second, to get the results. They are highly efficient, but not flexible, and statistic only. And this is why we believe the community needs a new tool, because good tools are prerequisites to superb work. But the first question is, how a good GPU kernel profiling tools looks like? In this work, Neutrino mainly targets 3 of them: fine granularity, versatility, and programmability. For fine granularity, the simplest example is the start and the ending time of the block. So you may ask, OK, end minus start give us the elapsed time. What else? If we have the fine-grained data, we can try to sort the blocks scheduled to the same computer units in order of their start and ending time. And we can do the inverse. Start minus the previous end give us the scheduling cost to dispatch a new block. This scheduling cost is highly overlooked. For example, the simplest line of torch.zeros have 20% scheduling cost. And this insight leads to a very simple solution and amazingly 30% performance improvement. So fine-grained raw data allows new opportunities. Our second design objectivity is the versatility. Here we refer to covering both the time and the value profiling. This is in contrast to previous profilers that are either value only, that can only give you memory allocations, or time only, that can only give you the memory pressure across the time. In Neutrino, we try to combine these two together to open a new profiling dimension to understand the runtime behavior. Our third objective is programmability, to allow developers like you to customize the props for your own needs and switch the prop using the same infrastructure like the block scheduling cost prop and the memory access prop in the previous examples, and easily in Python domain-specific languages. To achieve these 3 goals, we definitely need to overcome many challenges. And I would like to highlight 3 here. First, GPU kernel is atomic to operating system. Mostly, you can only launch it and wait for it. There's no host tech stack anymore, like eBPF or ptrace. Second, we lack the architecture support, particularly the programmable timer interrupt. This is the basis for sampling-based providers like Songlin. And third, and most important, we have a very complicated ecosystems. I tried to put some logos here, but this is far from complete. However, compatibility matters a lot for general-purpose GPU kernel profiler like Neutrino. Our design choice started by sorting out this complicated ecosystem into 2 branches from the perspective of compilation: the ahead-of-time compiled CUDA C++ and just-in-time compiled domestic languages. We identify that these 2 branches will merge at a layer of parallel assembly and will finally dispatch to particular hardware at a layer of the driver. So our design choice is to use the parallel assembly as a probing layer, because this is the highest common layer of the ecosystem, and use the driver as the runtime support, because this is the lowest common layer in the ecosystem. We also identify that using assembly leads to a lot of features. For example, we can easily capture hardware details, like the MMA can be mapped to tensor cores, and we can easily do the timings by subtracting the device-side clocks before and after the segments you want. We can easily do the value profiling by reading the register values. So our design choice can be summarized as assembly as a probing interface, the driver as the runtime interface. Based on such a design, we've propose an eBPF-inspired probe interface. Neutrino probe is consisted of 3 parts. So first, it's a snippet of a few lines of code. Second, the trace point is the instructions to be matched. And third is the structured map. By using such a simple program model, we can support a variety of profiling tasks, as demonstrated here. And I would like to highlight 3 key features we provided. First, we extend many helpers, like the eBPF helpers, to extend the probe functionality, like the ADDR in this example. That will be translated to the real memory addresses in the runtime. Second, multiple probes in Neutrino can combine together to support more complicated workloads, profiling tasks. And third, we provide the context registers as a temporal storage for the probe cooperation. For example, the start register as highlighted in purple in the block scheduling examples. It has a value as a starting clock at the beginning of the thread, and it will be context till the end of the thread to be processed by another probe. This allows a next level of programmabilities. By taking such a formal design of the probe, we can choose a very, very simple probing method. That is to direct inject the probe to the raw execution. For example, this is the execution of the program from left to right as guided by the program counter. What Neutrino do is simply inject it without the protection of a stack or any other method. But we still want to emphasize such an execution model is still virtualized because we can have the time separation. Since the execution within the SIMT threads is sequential, so there won't be any time overlapping. And by formulating a logically independent register groups, we can also achieve the resource isolation, that the execution of the probe and the program without no interference. The second design challenge is about persistence, or more particularly, the metadata, like the thread index and block index. They are very useful for analysis, but can also be very storage hungry. Guess what? 24 bytes without doing anything per thread. So in Neutrino, we try to formulate our maps to a tensor-like layout and give every thread a map. This allows to achieve the metadata efficiency because the thread index can be derived rather than being saved. And we can also achieve the lock-free because each thread has its own map without interference, so there's no need for a lock. And there are also many other designs like the verifications. Please check our paper for more details. We implement Neutrino as a command line tools, like the Valgrind or BPF trace. When invoked, the entry will load the probe and compile it to assembly and set it as an environment variables. Then it will fork and execute the sub-process to do the profiled program, with the hook driver being injected through the LD preload. The hook driver will continuously to capture the GPU workloads, particularly the memories and the code, to launch the kernels. For every unseen code, it will launch the probe engine to do the probings and assemble it back to machine code to launch on a real GPU. After execution, the hook driver will dump the traces to the disk and give back control to the user program. For the internal details, hook driver mainly is motivated for a practical issue. We don't have the code because we are not the compilers. All right. But we identify that code must be loaded through the drivers before really executed. So we built a hook driver leveraging a key idea of formulating a driver ELF with exactly the same signature and user FCN inside. Based on this mechanism, we built a comprehensive workflow centralized with 2 internal storage for image and for the kernel. We also built a probe engine to instrument the GPU assembly according to the probe definitions, as well as the DSL compilers that takes the Python DSL that I exampled above as a front end, translated into an eBPF-like intermediate representation and do the generation to platform-specific assemblies. We particularly designed the IR to eBPF-like to feature the reusing of mature eBPF toolchains. There are more unique utilities and extensions. Please check our paper. Yeah. Then we want to visualize the neutrino traces. or maybe the most comprehensive page reference map, like this one. The problem in GPU is that we usually have more than one thread, so we have multiple maps. And the simple aggregation actually does not work. Why? Because the index between threads are not synchronized. There's no guarantee that threads will be executed in the same paces. Therefore, in Neutrino, we propose DMAT. The solution is to use the physical time as a concrete anchor for safe aggregation. And we also use the colors to represent the densities as the color depths and the different tensors in different colors. This allows us a very intuitive representation like the right one. By using DMAT, we can understand the GPU kernel visually. For example, by comparing the DMAT of the flash attention V1 and the memory-efficient attention, we can identify that the flash attention is more memory efficient since the access to query tensor, as highlighted in blue color, was saved. We conduct very comprehensive analysis evaluations to validate the execution correctness and the profiling accuracy. We also show that Neutrino has a very low overhead to nearly 1.04% times for smaller probes. And in some cases, the probe can even accelerate the execution with a very high usability to profile the whole model. Please refer to our paper for more evaluation details and results. We want to present you a very interesting case study to demonstrate how Neutrino can be used to understand the runtime behavior in GPU kernels progressively. So GPU instruction dispatcher will schedule a warp from its candidates per cycle to resources like ALU for execution. And in practice, there will be more than one candidate to avoid the stalling cycles, and there will be two cases for these warps, like a block exclusively take the whole SM or share with another blocks. These are easily configurable via the non-warps configurations in Triton and other compilers. Our common understanding about this effect is like they have a very near performance. But however, if we visualize in DMAT, we can find it totally different. The exclusive blocks has a very uniform memory access pattern, as stated by the algorithm. But however, for shared blocks, we got a weird sparse, then dense pattern. Oh, how come? We're using the same code, just change a configuration, leads to such dramatic changes. With Neutrino, we can first try to quantify the tailing effect by plotting the cumulative distribution function of the block elapsed time. And we can find that the shared block has nearly 50% of the tailing effect. This is unknown before. And this is not the end. With Neutrino, we can do more. Like we can sample the progress within the execution of the block and find that each block was started by a slow stage and jump into a fast stage at some point. And it is the existence and the duration of the slow stage that leads to the tailing effect. And even more, we can align the blocks scheduled on the same SM, and we can find that the jumping point from the slow stage to the fast stage is exactly when the previous block in the fast stage terminates. This pinpointing a potential implicit FIFO-like prioritized scheduling in the GPU instructions. And it showcases how Neutrino opens the window for observing the runtime behavior of the GPU kernel, a well-known black box. I would like to finalize my presentation with something easier, like how to use Neutrino. Neutrino is installable as a Python package, and it is well documented. It comes with a very high compatibility. We support CUDA and RCM from AMD. And for software, we support nearly everything. JAX, Triton, PyTorch, and everything built onto this, like the Hugging Face. There's definitely more to support. Please reach out if you are interested. As a conclusion, in Neutrino, we envision to profile the GPU kernel like eBPF for the OS kernel. We present a programmable interface for fine-grained and versatile GPU kernel profiling. We allow users to simply write Python DSL to probe the GPU kernel at the runtime with very high compatibility. And we bring out many profiling tools like DMAT and many new insights for you to explore. Here are the contact informations. Thank you for listening. I'm open to questions.